Okay, so as we were saying, these are three different views of the structure of D-glucose. I think the only one that's important for you guys to remember is maybe the straight chain form. These are a little bit complicated. Though I did in the class notes explain how it is that you get from the straight chain form to these cyclic forms. And of course, for both the chair form or chair projection and the so-called Haworth projection, that is a Haworth projection, H-A-W-O-R-T-H projection. Not to be confused with the Fisher projection, not to be confused with the Newman projection. There are certainly no shortage of people who had projections named after them. But this type of drawing of sugars, I think you'll find to be very common, especially in biology and biochem classes. And there's good and there's bad about it. What's really nice about the Haworth projection is it's very clear whether groups are pointing up or down, you know, above the ring or below the ring. That part's very clear. What's not so clear is the bond angles. The bond angles are all screwed up. So that's why that's the thing that the chair form gets right. And as I've said, if you understand that cyclohexane can exist in these chair conformations, you've got all you need to know. All we're going to do to turn it into glucose is change one of the CH2s to an oxygen. And so this is another way of drawing the structure of D-glucose. So here, all of the bond angle, I could quibble a little bit with some of my bond angles. This is a little too close to a right angle, but it's close enough for jazz. In any case, so the bond angles are certainly much improved in the chair form over the Haworth projection. And that's all fine, but the information that's a little harder to come by with the chair form is being able to tell whether something's up or down, right? We talked about this with cyclohexane chair forms. The axial positions are very clear. This is obviously down, this H is obviously up, that H is obviously down, right? And we said a lot of these things. Remember we said how the axial positions alternate up, down, up, down, up, down as you go around the ring. And in fact, so do the equatorial positions. The trouble is the equatorial groups, it's difficult without practice to tell whether they're up or down. And so generally what I advise students to do, you know, let's say we wanted to know what this OH is, whether it's up or down. What I generally advise people to do is if you're having trouble, look at the other group that's attached to the same carbon, the one that's axial. That's a cinch. This H is definitely down. I don't think anyone can doubt that. Therefore, this OH must be up because you can only have one of each. So that's the tricky part about up-down versus axial equatorial is they don't go together. There's no necessary correlation or correspondence, if you will, between up-down and axial equatorial. It depends on which carbon you're looking at. In any case, for both of these drawings of the cyclic form, I've drawn, I guess you would say, the alpha anomer, right? Because the OH group is pointing down on both of them. So down is alpha because the vowels and consonants don't go together. So you've got both, you've got the alpha form, you've also got the beta form. So the one where the OH is pointing up is also present in solution. And then you've also got the two furanose forms with 5-membered rings. Again, alpha and beta on both of those. And I've never even bothered to memorize those. I don't work with them really. Though I mean, I would like you to be aware that all 5 of these things are present in solution, and there's a rapid equilibrium between all of them. I think you would find, though, that there's very little of the open chain form left in aqueous solution, that most of it at any given time is going to be in one of the cyclic forms, either one of the 2 pyranose forms, which is this one, or one of the 2 furanose forms. So certainly I would like you to be aware that all those things are there. But I think the only structure that could possibly benefit you knowing down the road is the structure of glucose. So, but I wanted to make sure that I showed you where all of these, where all of the carbons went, and that I showed you the versions with all of the carbons numbered. And we have other things to talk about today too. I want to say at least a little bit about reactions. of simple sugars, which we're going to find, by the way, they have the same functional groups that we've talked about already. We've talked about alcohols, and we've talked about aldehydes and ketones. Completely unsurprisingly, the alcohol groups and the aldehyde or ketone groups in sugars do the exact same things. So that's why I choose to go in the order that I do, because I hope it's at least somewhat fresh in your memory. I'll just, like I said, I really don't care if you memorize the chair form, but one nice thing about the chair form that I know I ended class with the last time is when you're talking about glucose in particular, for some reason, again, apart from carbon 1, the anomeric carbon or the formerly aldehyde carbon, that can be either axial or equatorial, either up or down, depending on whether you're beta or alpha form, respectively. But all of the other remaining carbons in the ring, carbons 2 through 5, and every last one of those 4, the larger group is equatorial. So I don't know why that is. I feel pretty certain that's just a coincidence, but it certainly is a very nice coincidence. And so even if we were memorizing these two, or you know, which we're not, if we were in Chem 228, we would be. But I'll just let you know for what it's worth. I've never bothered memorizing the Haworth projection, the way to draw that, because I just get it from the chair form, which is easy to remember because carbons 2 through 5 for glucose, everything, all of the bigger groups are equatorial. So I just get that down and then copy the Haworth projection from it. Here in carbon 1, this OH is pointing down, so I do so here. On carbon 2, the H is up and the OH is down, so there you go. Carbon 3, the OH is up and the H is down. There you are. Carbon 4, the OH is down, the H is up. There we go. And again, on carbon 5, the carbon 6 CH2OH group is up, and the hydrogen attached to that same carbon is down. And I sort of squished my hydrogen in there, but I think you can maybe see it. So, so that's basically this. I've never bothered memorizing the Haworth projections. I don't see the need. I just remember the chair form. Good. So again, everyone, please register your attendance. We're only taking attendance today since we did a polling session last time. So one other point that I wanted to make, and it's the reason why I think if you know glucose, that's pretty much everything you need to know. It may be that in an upper level biology or biochem class, you might have the pleasure of memorizing all 8 D-aldohexoses, so glucose, D-glucose, and its 7 other friends. I never make any of my students in 228 either memorize all of those, because there's no point. There's no point to it, because if you know glucose, you automatically know all of the others. For instance, let's say we wanted to know what D-mannose looked like. All we would need to be told, and I only know this because, as you probably saw, I looked it up right at the beginning of class. All you need to know is that D-mannose is just like D-glucose, except it differs at carbon 2. So at carbon number 2, it is the opposite configuration. Otherwise, it's identical. Well, that makes it very easy to draw. I'm going to try drawing it like this for a change. Kind of like that. Maybe I should do it that way from now on. So here's carbon 1. That's the same. That's the aldehyde. At carbon 2, it's the opposite. So we'll want to put our OH over here. By the way, a note on that as well. I'm glad I'm going over this again because I feel I sort of rushed over a lot of things. Take note how I'm being careful to draw HO to show clearly that the oxygen is what's attached to the carbon over here. And yeah, I think it would be wrong to write OH instead of HO, because that indicates to me that whoever drew it is not thinking of atoms connected to each other. But that's carbon 2, so that's where the difference is. And the rest is the same. So instead of right, left, right, right, it's left, left, right, right. And of course, over here, the one I'm drawing right now, that carbon right there, that's your all-important penultimate carbon. That's the one that determines that you're looking at a D sugar, because the OH is pointing to the right, CH2OH. And if we wanted to, the same would be true for the other forms. Maybe I'll just draw the chair form. Maybe this time I feel like drawing beta. So that's carbon 1. Over here is carbon 2. So this is where it's going to differ from glucose. Now my OH will be axial and my hydrogen equatorial. Other than that, everything else will be the same because that's carbon 2 over there. This is carbon 1. So OH down over here. Hydrogen. What am I doing? Just kidding. OH over here. Hydrogen over here. Hydrogen up, OH down. And CH2OH pointing up. That's the equatorial group in this case, and the hydrogen pointing down. All I mean by, showing a space in that bond, I'm just trying to increase the illusion that this bond is behind this carbon-carbon bond. So that's why I see no point in any of my students memorizing all the other 7. You got mannose and lysose and talose, and there's 7 others besides glucose, all of which have certain roles. I couldn't tell you what they were, but I see no benefit to be gained from memorizing all 7, because if you know glucose, you automatically know all the others. And by the way, it would not be a complete waste of your time if you drew the Haworth projection of D-mannose. And again, you can keep it in the beta form like we have here, just to get the practice in. See, and by the way, you can do that just by looking at the Haworth projection of glucose if you want, and simply inverting whatever's going on at carbon 2. So that would not be a bad little exercise if you have a spare few minutes, say this weekend. But I think that's all I really need to say about that. But I wanted to be sure that I explained those structures a little bit better. So as long as we're aware again that in solution, in aqueous solution, for any one of these, glucose or any of its 7 friends, you've got 5 different species in solution. You've got a teeny little bit of the straight chain form, maybe 2 or 3% at any given time. You've got both pyranose forms, the alpha and beta anomers, and you've got both furanose forms, again, alpha and beta anomers. So, and that's a rapid equilibrium, by the way. You've got furanose forms opening up to the straight chain form and then going back to furanose or going back to pyranose. You've got pyranose forms opening up. There's a rapid equilibrium between all of those. So this time I really do mean an equilibrium. This is not a resonance situation. There really are equilibria that by which all of those things interconvert. And that I think is the best way to understand, at least as far as I can tell, the behavior of these compounds in water. Good, so let's see, I think I can pretty much leave it at that. I think I'm scheduled to get through 1610 today. Yep, that's correct. So that means we're going to go over some of the reactions of simple sugars. And again, like I said, I don't think any of them are going to surprise you. So I want to talk about esterifying them. That actually is going to be a somewhat new reaction for us, since we're really going to cover esterification more in detail in chapter 10. But I don't think it's a reaction that's going to surprise you at all. We'll also talk about forming what they call glycosides, or forming ethers on those OH groups. Well, we already know how to turn alcohol groups into ethers. Williamson ether synthesis. We talked about that in chapter, help me out, 8? I think that's right, the chapter on ethers. Yep, so the same thing's going to be true here. Just a variation on that. And then we'll end up with some redox chemistry of these sugars, which is also relevant since those sorts of reactions also happen in living systems, not using the reagents we're going to be talking about. We'll talk about how to do it in the laboratory. But I think if we can get through that much today, I'll be pretty happy. And if by chance there's some time left over, which there never is with me, but if there somehow is, maybe I'll give some examples of reactions of alcohols or of aldehydes and ketones, something like that. Good. Yes, we are recording. Good. So any questions then before we go on? Maybe I shouldn't have deleted that. I'm going to be sad when I go back to teaching with chalk on a chalkboard that there's no Control Z. Also, I've realized if I got nothing else out of this term, and I think I've gotten a lot out of this term, but even if I had got nothing else out of this term, at least I've gotten better at drawing and writing with a mouse. You know, got to take what you can get. Okay, so what if we try to do a Williamson ether synthesis with a sugar molecule? Let me actually get my D-glucose back here, and I'll use the pyranose form, and I'll draw it in the chair conformation because for me that's easiest. And I could choose alpha or beta. This time I feel like it being beta. So again, all of the hydrogens are axial, and all of the larger non-hydrogen groups are equatorial. These are all going to be OHs, of course. This one too. And then CH2OH in the equatorial position. And then the hydrogen going down here. Well, we learned in chapter 8 that if you treat an alcohol with a base and the presence of an alkyl halide, preferably primary, then you will get an ether. It's nothing more than an SN2 reaction. We called that the Williamson ether synthesis. The only trick is, look at all these OH groups. Is there any way you can select for like just this one or just this one? And the answer is no. Using a Williamson ether synthesis, there's no way to select for just one. But if one were to use a large excess of some alkyl halide, preferably primary, then you will do what's called an exhaustive alkylation. Because we're exhausted. No, you know what exhaustive means. It means complete, total, 100%. And so as a result, we'll perform a Williamson ether synthesis on every single one of these OH groups. So let's say for instance, we're using, again, you do generally want some base around. It can even be an organic base like pyridine or say triethylamine. Can I go ET3N for triethylamine? That's a base, right? You've got your alkyl and nitrogen over here. And let's say we used an excess of 1-bromobutane, just because I can't think of anything more exciting at the moment. Well, that will alkylate or butylate every single one of those OH groups. And I would expect to get a product with all of those OH groups having been converted to ethers. 1, 2, 3, 4. And we have hydrogen up here. Instead of OH, it's O-butyl. 1, 2, 3, 4. Oxygen, 1, 2, 3, 4. Gonna have to dodge that other molecule here. 1, 2, 3, 4. It works. CH2O butyl. 1, 2, 3, 4. And the hydrogen down here. So I would expect to get a product looking much like this. But this is nothing new here. This is not a new reaction for us. We already knew you could do that type of thing with alcohols. And so all we're observing is that you can do the very same thing with the alcohol functional groups on a sugar. That's all there is to it. Or let's see, maybe give another example. Let's do galactose. Oh, I have an even better idea. Let's do a straight chain form. Actually, am I about to lie to you if I do this? Let me just make sure, because that does beg certain questions. Nah, I think we can go with this. And galactose is just like glucose, except it differs at carbon 4, 1, 2, 3, 4. So instead of right, left, right, we got right, left, left, right. And I don't care if you memorize that that's what galactose is. It's one I've used on a bunch of Chem 228 exams, so I happen to remember that one. But if you ask me what talose was, or xylose, or allose, no idea. So there's your D-galactose. And let's say that we treated this with an excess of benzyl bromide. Oh, that's boring. Methyl iodide. I always use benzyl bromide. But I probably have students going, on the exam, he'll put benzyl bromide, you know, that type of thing. And let's say, again, we use triethylamine as the base, or you could use even KOH or sodium hydroxide, doesn't matter. As long as you have some base to take up the protons that come off of the alcohols, they have to go somewhere. So you need some base to pick those up for you. And I would expect at least if you're given this structure for starters, I would think it would be reasonable that you would then methylate every single one of those OHs. So instead of OH, you've got OCH3. OCH3. I screwed up the spacing, but I think I might be able to win on this one. I love it when things work out. So CH3O. Same thing over here. And OCH3. So again, it's an exhaustive alkylation. By the way, just in case anyone's curious, why did I choose methyl iodide instead of methyl bromide? Well, methyl bromide or methyl chloride would be fine if you were to put that down in an answer also. It turns out, though, in real life, we like to use methyl iodide because methyl iodide's a liquid at room temperature, and methyl bromide and methyl chloride are gases at room temperature. So it's a pain to use them. It can be done, but you'd have to get a gas cylinder and a big cold condenser with dry ice acetone cooling or something like that, maybe even liquid nitrogen if you're really unlucky. It can be done and has been done, but if we have a choice in real life, we'll use methyl iodide. It's much easier to measure out a liquid than a gas, I think you'll agree. So there you go. But this is nothing other than the Williamson ether synthesis, which, by the way, that's in section 8.5, if you'd like to review that, which is in the class notes. I put that in the class notes too. But if you've forgotten about the Williamson ether synthesis and want to check that out again, I should mention another way that they often do this is instead of using a base, it doesn't really matter which base you use, by the way, but instead of using a base, another alternative is to use a silver 1 salt, like silver 1 oxide or silver 1 nitrate. And the reason they use those is, as you might recall from Gen Chem, the silver 1 ion loves halide ions, and they form exceedingly insoluble precipitates. So for instance, if you used either one of these silver 1 salts, you would also get out at the end silver 1 iodide, which is completely insoluble in practically everything. And so that crashes out of solution. You get this brilliant yellow or orange silver 1 salt, and that drives the reaction forward. That gives these OHs the means to react with methyl iodide. Since you're pulling the iodide, you're pulling that out. And that again drives the reaction forward by Le Chatelier's principle. One of the things Le Chatelier's principle says is, last day we didn't use, the triethylamine is not a catalyst. We used other bases. We might even have used really strong bases that deprotonated the alcohol completely. It doesn't matter. It's the same reaction. And the end result is the same. Or like I said, you don't even need to use a base at all. You can just use a silver 1 salt, and you will get the silver 1 halide salt, and that will drive the reaction forward by Le Chatelier's principle. So any of the above is fine. Doesn't matter whether you use a stronger base even still than triethylamine or pyridine, doesn't matter. I guess my point here is just that this is the exact same type of reaction as in chapter 8. It's just a variation on the Williamson ether synthesis. So this is exhaustive alkylation. I think we used sodium metal to form O-, and you could do the same thing here. You know, it doesn't really matter. But all of these are variations on the same thing. So yeah, that's basically it. So we call that exhaustive alkylation of these simple monosaccharides. Good. Make sense? Other questions on that? So another exhaustive, because we're exhausted, another similar type of reaction, which we will learn more about in chapter 10 coming up. Instead of exhaustive alkylation is exhaustive acylation. You may recall that word acyl. We defined that way back in chapter 4 when we talked about adding an acyl, or rather substituting a hydrogen on a benzene ring with an acyl group. So remember, an acyl group is essentially RC double bond O. And then whatever else is attached to the other side of the carbonyl, that can be pretty much anything. But this type of group is called an acyl group. And it's certainly possible also to replace the hydrogens on a sugar molecule with acyl groups. And in the end, we will get esters. So let's go back to maybe our glucose. Maybe today we've got the alpha anomer, where the OH is downish. And let's say we wanted to acylate all of those oxygens. Well, the reagent of choice, just want to be sure that I just want to be sure I do this. Okay, just wanted to be sure I do this the same way as in your book. I don't want to confuse you. But you actually have your choice of reagents. Going to be an awful lot of silence in the video for today. So here's our glucose. And let's say that we wanted to convert all of the OH groups to acetate groups. And so in the end, we'd have O, C double bond O, CH3. And of course, we would have no choice, but we would want to do that to all of them. Because again, there's no way to make a reaction like this selective. You can't acylate just one of them. You're going to get all of them. And Oh, that looks dreadful. Just trying to make it look a little bit better. Whatevs. I think you see what I mean. So we'll put an acetate group over here, also over here. C double bond O. CH3. This is done a lot, by the way, my understanding, those who work with sugars on a regular basis. CH2O acetate. I feel like ester derivatives are useful. So I've been told. I couldn't really give you details on what they're used for in the biz. But let's say you, oh, I forgot my hydrogen. Let's say you wanted to make this compound. You have two choices. You can use an excess of either the corresponding acid chloride or the corresponding acid anhydride. And again, it's best also to use I'll draw that out again on the side bigger. Again, you also want some base to pick up all of the HCl that you will make. Triethylamine is fine, pyridine is fine. So the reagent used, the reagent of choice is either the corresponding acid chloride, which looks like this, or the corresponding acid anhydride. And this is the one that you'll use if you want to make an acetate ester. There are other esters. You can make a propionate ester or a butyrate ester or a benzoate ester. So the CH3 can be swapped out for any other group that you might like. But the other reagent that you can use is the corresponding acid anhydride, which looks like this. What do you mean? This is a small molecule, smaller than this. And even whether, by the way, there's a lot of stuff going on here. But I think my point is, I hope you can appreciate at this point in the term, yeah, that's a big molecule. But when you break it down into its parts, it's doable. You can at least understand what all the different parts are. Maybe I don't really care. I don't know that I care very much whether you can draw this molecule. But I think whether or not you can draw it, you can understand it. We understand what a sugar is now. We know what ester functional groups are. It's manageable. This one here certainly is manageable. That's a small molecule by any stretch. So my point here is you can use either the acid chloride or the acid anhydride. The only difference is in the end whether you get HCl or the corresponding carboxylic acid. In this case, it would be acetic acid. Either way, you want to have some base around to neutralize the acid. But we call reactions of that type exhaustive acylation. And again, I don't know of a way just to acylate just that OH or just this one, or I don't know of a way to do that. I don't think it's possible. Next time, I think we'll learn that you can do reactions just on the anomeric OH, the one that's in carbon 1. That you can do. That's next time, though. And it's very different. So it's possible to, the second reagent, these are acid anhydrides. If you take acetic acid and cook the snot out of it and remove the water, you'll get the anhydride. Anhydride meaning literally water has been removed. So this is an acid chloride or an acyl chloride. And we've seen examples of these functional groups at other times, I believe. At least I think so. Good. And either one of those is fine. Doesn't matter if you use acid chloride or anhydride. You might ask, can this be a bromine instead of a chlorine? And the answer is yes, but acid bromides are a lot harder to get your hands on. They're much less stable, and there's very few of them commercially available. But acid chlorides are very common, very cheap, and very easy to order. Again, if you're connected and have the ability to order chemicals for your research group, then yes, you can get them. But either one of these are pretty common. Actually, if you ever made aspirin in like a high school chem lab or something like that, I have little doubt that you used acetic anhydride, which is this one here. So that one would be acetic anhydride. But you don't have to use acetic anhydride. You can use a different acid anhydride. You don't have to make acetate esters. You could make, like I said, you can make propionate esters or benzoate esters. So you just swap out these methyl groups for whatever the alkyl group is in whatever you're given. That can vary. But if you've ever made aspirin, you took salicylic acid, which is pretty easy to get, and well, heck, this is not part of this chapter's information, but it's not like I don't have time today. And we're going to talk more about this in chapter 10, so it will be relevant eventually. But salicylic acid looks like this. And I don't care if you memorize that, but that's salicylic acid. This gets used in its own right. Do you remember you ever used fluoride-containing reagent? Even rarer, acyl fluorides, there might only be one or two that you can get your hands on. And I would be scared to use those because now you're making HF, and HF eats glass, by the way. So I would stick with the acid chloride. In any case, what you probably did is you probably used acetic anhydride, since both acetic anhydride and acetyl chloride are nasty, but I would rank acetic anhydride as being about 10% less nasty. At least if you get any up your nose, you're only going to make acetic acid up there as opposed to HCl. But both are pretty nasty. But you probably used an excess of this and you wound up making the acetate ester on the phenolic OH. Of course, it doesn't touch the carboxylic acid group. So we'll talk about this in chapter 10. But same exact way you'll make the acetate ester. And that's aspirin, acetyl salicylic acid. A relatively unimportant molecule that a tiny insignificant company called Bayer made a tiny bit of money on, about 100 years ago. This compound is salicylic acid. And again, I don't care if you memorize that, but that compound is important in and of itself. It was, 4,000 and 5,000 years ago that people were extracting that. They didn't know what it was, but they were getting that out of the bark of willow trees. And they discovered that if they chewed on that bark, that it would help to diminish pain and fever. So salicylic acid is an analgesic in its own right. It's just quite a bit harsher on the stomach than aspirin. Aspirin, some people have troubles with their stomach with aspirin too. Salicylic acid's even worse. And you'll be able to appreciate that when I tell you further that salicylic acid is also available over the counter in preparations for, it's for external use, and it's used to remove things like warts and corns, things like that. So it's chewing on the skin. It's pretty nasty. But you probably did that if you took milk of the poppy. Really? I thought I was under the impression it came from willow tree bark. Be that as it may, so this is all closely related. We'll go over that more again in chapter 10, so we'll close the loop on that. But we'll learn as time goes on that that you can treat alcohols with either acid chlorides or acid anhydrides and get esters that way. It's not the only way to get esters, but it is one way. Good. I think I've probably another way to cure pain. Well, let's talk about legal ways of dealing with pain. Good. Certainly, all the better if you can get it over the counter. Anyway, that gives us probably just enough time to go over some redox reactions of simple sugars. And again, these are going to be things we know already, I think, or at least analogous to things we know already. We already know, I'm just going to use glucose here again because actually, no, I won't use glucose. I'll make up a 5-carbon sugar because it just doesn't matter. Let's do right. And do I know what that's called? No idea. But I know it's an aldopentose, and I know it's a D sugar because my penultimate OH is pointing to the right. So that much I do know, and I think you do too, or at least you will. We already discussed reagents like sodium borohydride. We discussed how either sodium borohydride or lithium aluminum hydride, generally this is done in some sort of aqueous alcoholic mixture, aqueous methanol or aqueous ethanol, and that will reduce the aldehyde to a primary alcohol. We know that already. We learned that in chapter 9. And everything else will, of course, be left the same. Of course, sodium borohydride doesn't touch alcohols, they're already reduced. And you get a structure that looks like this. So that type of reaction is very straightforward. Another way to do the same thing is with lithium aluminum hydride, which is we discussed in chapter 9. For the purposes of, you can write as a second step, either water or H3O plus, doesn't matter. We said that for the purposes of ketones and aldehydes, these two reagents are interchangeable. They both will reduce an aldehyde to a primary alcohol. That's not going to be the case for esters and carboxylic acids when we get to chapter 10. But for aldehydes and ketones, it doesn't matter which reagent you use. In real life, I would prefer to use sodium borohydride first because it's less reactive. I think I've given you the principle that in general, we try using the smallest possible hammer first before we get out the big one. This one is a much less reactive, much milder reagent, much easier to deal with. You start using LAH, you start getting fires. I mean, you can, and trust me, fires sound great until you get one that you didn't want to have. So I sometimes have difficulty convincing students of that. But unless you were trying to do it for some sort of whiz-bang, demonstration where everything's highly controlled, outside of that, believe you me, fires and explosions are bad. They're bad things. They can hurt or even kill people. But be that as it may, this is a reaction we know already. We already know that you can reduce an aldehyde group to an alcohol functional group using one of these hydride reagents. Now, these types of compounds are called alditols or sugar alcohols, and they are useful also in their own right. They're also called sugar alcohols. And if you've ever chewed sugarless gum, well, actually, I guess all gum now is sugarless, at least I hope so. I don't think sugared gum, I'm pretty sure they got rid of that in like the 70s. I remember it, I was a very small child, but I think, correct me if I'm wrong, but I think all gum is sugarless now. Because finally, around 1970, some dentist said, maybe we shouldn't have children chewing on this stuff all the time. Maybe it's bad for their teeth. But alditols are used, among other things, as artificial sweeteners. And so, in addition, from what I'm told, I'm not a dentist or anything like that, but I'm told that they're also good for oral health because all those nasty bacteria in our mouth do not like alditols. They tend to kill off those bacteria, at least to an extent. So that's why you find them in sugarless gum or those mints, you know. So you tend to find these things quite a bit in over-the-counter things like that. What about oxidation reactions? Can we oxidize sugars? Yes, you can. And the reagents here always surprised me a great deal because they're so simple, and you wouldn't think that something that simple and straightforward could do such a very particular reaction. Let's use our same 5-carbon sugar, whatever it might be. And I'll reiterate, you see drawings like this quite a bit in biology and biochem textbooks. I'm not a fan. At least in here, let's draw in the hydrogen. Otherwise, it looks like a methyl group. You see what I mean? It's confusing. So at least in this class, let's draw in those hydrogens. And it turns out that you can treat any sugar, whether it's 3 carbons, 5 carbons, 15 carbons, you can treat it with aqueous bromine, of all things. And all of the halogens are good oxidizing agents, whether chlorine or bromine or fluorine in the extreme, or iodine also. Bromine seems to have just the right reactivity here, but they're good oxidizing agents because in the elemental form, of course, these bromine atoms have an oxidation number of 0 because it's a pure element. Well, the bromine would much rather be -1. So the bromine wants to get reduced from 0 to -1, so it's going to oxidize the other guy. And let me just make sure I'm not lying to you. Yes, so all this does, and again, I always found this very astonishing. It oxidizes the aldehyde group to a carboxylic acid group and doesn't touch anything else. Doesn't touch any of the other OHs on the chain, doesn't touch the primary alcohol at the other end. I think that's absolutely crazy, almost to the point of being unbelievable. Normally, really selective reactions like this, you would expect would be the domain of an enzyme or something like that, you know, something, or at the very least, some stupidly expensive, you know, rare earth element catalyst, you know, something that you're paying $300 for 50 milligrams of it. No, it's just aqueous bromine. But believe it or not, that's the case. And I always get these backwards, but I have it in your notes. This type of compound is called an aldonic acid. But that's always going to be the case, regardless of what you're given to start with. Bromine and aqueous bromine is a relatively mild oxidizing agent. It oxidizes the aldehyde to a carboxylic acid and doesn't touch anything else. Everything else remains the same. I think that's pretty amazing. And then one last reaction, and there you go. I actually did it. I used up all the class time. Sometimes I amaze even myself. Let's start with the same sugar. There is a somewhat stronger oxidizing agent, namely warm nitric acid. Nitric acid is a really, really good oxidizing agent. And for the reason there, if you look at the structure, you'll see nitrogen in the +5 oxidation state. It would much rather be taken to a lower oxidation state, like +3 or -3. And so this just uses nitric acid. You know that formula, right? HNO3. And usually it's warmed. And in this case, you get a little bit more oxidation. This now will oxidize the aldehyde functional group to a carboxylic acid. And it also oxidizes the primary alcohol at the other end of the molecule to a carboxylic acid. And other than that, it doesn't touch anything. All of the OHs on the intervening carbons, it leaves them alone, which again, I think is pretty interesting. And again, it doesn't matter how many carbons are in the sugar. 3, 18, 157, all of those other intervening OHs, whether they're on the left or the right, they don't get touched. And this type of compound is known as an aldonic acid, sorry. And these types of molecules are called Aldoric acids. Frustratingly similar name, Aldonic versus Aldoric. And these are all very commonly done, so I'm told, it's not my area, but these are all very commonly done transformations on sugar molecules. And with that, we did it again. We got to the end of another class. So any last questions on any of that? But we'll close the loop on sugars on Monday. And then I guess we have our 4th exam coming up. Woohoo! Is that Friday? Ah, the following Monday. Excellent. That's so good. You have no idea. I'm glad I put it off one day because Friday is my 227 exam. So excellent. In that case, have a great weekend. I will see you all on Monday.